Hi, everyone. Welcome to section 2.5. In this section, we are going to be talking about rational functions and how do they behave. Let's begin by talking about the notation. How do we apply notation describing an infinite behavior for a function? So we are going to start by defining what a rational function is. A rational function is let P and Q be polynomials where Q of x is not equal to 0. A function f is defined by the quotient or the division between two polynomials, p of x and q of x. Now, what happens as x approaches c from the right side, but not equal to c? What happens is it approaches c, a value, where c is a value from the right or the left. Now, but it's not equal to, so it's just approaching. Now, what happens as x approaches positive infinity and what happens when x approaches negative infinity? So these are the four cases. We can have x approaches a value from the left, a value from the right, positive infinity or negative infinity. And let's look at some examples. Here we have f of x to be x minus 1 over x minus 3, where p of x is going to be x minus 1, q of x is x minus 3, where x minus 3 cannot equal 0. What do we notice? Well, what happens as x goes to infinity? Well, remember, if x is going to infinity, as x goes to infinity, it's going to approach a value. What value is it approaching? And the value that it's going to be approaching is positive 1 from above. What happens as x goes to negative infinity? So it's just going to this way. As it goes this way, then my function will also be 1, but now it's going to be from below. So where is my y value going? My y value is going to go to 1 from above. That's that orange. And the blue, it's going to be approaching 1, but from below. Now what happens as x approaches 3 from the right side? From the right. So let's go to 3. So this is x equal 3. From the right side would be this side. What happens as it approaches 3? Well, your function is going to go to positive infinity. So it's looking like this. Where is it tending to? It's tending to positive infinity. What happens as x approaches 3 from the left? Now, if it's from the left side, this is positive 3. From the left, it's going to go to negative infinity. So it depends where you're coming from. Are you coming from the positive direction of the 3 or the negative direction from the left or the right? Now, what do we see here? So as x approaches c from the right, the value will go to positive infinity. As it's approaching it from the left, it's going to go to positive infinity, but it's coming from the left side. Now, as x approaches c from the right, this will go to negative infinity. That means it looks like this. It's going to go to negative infinity as c approaches to the right. And what happens as c comes from the negative and it goes to negative? Well, that has this behavior. So again, as c comes from the right and it's going to go to positive infinity, it's going to look like this. as it's C coming from the left side, and it's going to go to positive direction. It looks like this. If it's approaching to the right, it's going to go to negative infinity. It's going to have this behavior. And lastly, if it's asking from the left of C and going to negative direction, it's going to look like this. Now let f of x be a rational. This is a rational function where p of x and q of x have no common factors than 1. Then we wish to find something called a vertical asymptote of f of x. That means we want to determine the real values of x where the denominator is 0, but the numerator is non-zero. So what we're looking at is we want to find what values of x give me 0 on the denominator. That will give us the vertical asymptotes, but the numerator is non-zero. So let's say we have number 2. We wish to identify vertical asymptotes. In order for this to happen, we want to know, okay, well, what values, I'm going to look at the denominator, at which x values am I going to get 0? That means you're going to have to factor the polynomial. So to factor, I use my x method. A times c, this is -5, -4. Two numbers that multiply and give me -5, but add to -4, that's -5 and 1. That means my denominator factors as x minus 5 and x plus 1. I set this equal to 0. That means at x equal 5 and at x equal -1, I will have my asymptotes, my vertical asymptotes. So VA stands for vertical asymptotes. So I will have vertical asymptotes and nothing cancels, right? So the numerator does not go away. Now let's look at question 2. We want to find the vertical asymptote. So you look at the denominator. So you look at x squared minus 2x minus 3, set that equal to 0 and factor. If I factor, I have a -3 and a -2, two numbers that multiply and give me -3, but add to -2, that looks like -3 and +1. So my numerator is x minus 3 and my denominator is x minus 3 and x plus 1. So note that I have an x minus 3 and an x minus 3. That you're going to say, oh, well, that cancels. But if you cancel, you still have a whole at x equal 3, because at x equal 3, I'm going to get a 0 in my denominator. So it's not going to be a vertical asymptote, it's going to be a whole. A whole occurs when you cancel the top and the bottom. Now the vertical asymptote will occur at x plus 1 set it equal to 0. That's x equal -1. So your vertical asymptote will be -1 and x equal 3 will be a whole. So you will have a whole at x equal 3 and a vertical asymptote at x equal -1. Now what happens if I have something like case number 3? So this is -8 over x squared plus 25. You're going to say, okay, well, you're going to set the denominator equal to 0. So that gives me x squared equal -25. But this is x equal plus or minus 5i. So be careful. This should only be real numbers. So because these are imaginary, no vertical asymptotes. There's no way I'm going to have a 0 on the denominator. No values of x will give me 0 on the denominator because they must be real numbers, not imaginary. So part 1 talks about vertical asymptotes. So this is a type of vertical asymptote as x approaches c from the right, as x approaches c from the left. Those are called vertical asymptotes. And then there is a explicit way to find avertical asymptotes from functions. Now, the second part is to identify horizontal asymptotes. So what is a horizontal asymptote? So a horizontal asymptote is if you have the equation y equal d. A horizontal asymptote of a graph of a function f is if f of x approaches d. So instead of x approaching the value, it's actually y. So it's going to be now y, or f of x approaches d as x approaches positive or negative infinity. So this means as x approaches positive infinity, your f of x will approach d. That looks like this, because x is approaching positive infinity and the y value is approaching a value d. So it could come from the right or it come from below. It could come from above or from below, but it's still approaching the same value d. Now what happens as x approaches negative infinity at a particular location? So you can have as x goes to negative infinity, as x approaches negative infinity, you can have it approaches d, or as x approaches negative infinity, and it gets you d. But they're both of those values, x is approaching negative infinity, and it's reaching a value d, again, from above or from below. Now, the way that you will be able to actually find a horizontal asymptote is by, let's say you have, again, p of x over q of x. What you have to do now is actually look at the degree of the numerator and the degree of the numerator. So if the degree of the numerator is greater than the denominator, then you do not have a horizontal asymptote. So an example would be if you have f of x is equal to x to the fifth over x to the third. See how the degree of the numerator is 5, the degree m is 3, so n is greater than 3, then you do not have a horizontal asymptote. Now, if n is less than or equal, less than m, then the y equals 0 is the x-axis, is a horizontal asymptote. So that's if you have f of x is equal to x to the third over x to the fifth. Now, n is equal to 3 and m is equal to 5. So 3 is less than 5. That would mean that your horizontal asymptote is at y equals 0, or the x-axis. Now, if the degrees are the same, so if the degree of the polynomials are the same, then you have then the horizontal asymptote, it's actually the coefficient, will be their coefficients. What does that mean? So I'm going to give you an example. If I have f of x to be equal to 5x to the fifth over 7x to the fifth, notice that the degree are the same. So then m is equal to 5, n is equal to 5. Look at the degree. That means that my horizontal asymptote is the coefficients. So it's going to be 5 over 7. So my horizontal asymptote will be at the line y equal 5/7. And that would be the value of d. That would be my horizontal asymptote. So what I'm going to do on the following questions, 5, 6, and 7, is focus on the degree of the polynomial. Okay, so let's do that together. So the first thing I have to look at is 3x and x squared. So 3x over x squared, the degree of the denominator is higher. So then it's going to be y equals 0, my horizontal asymptote. So notice that here at y equals 0, I will have a horizontal asymptote. And you can cross horizontal asymptotes. You cannot cross vertical asymptotes. So let me do a remark here. So you may cross or intersect a horizontal asymptote, a horizontal but not a vertical asymptote. They're different. So here in example 5, notice that this function crossed the horizontal asymptote. That's okay, but not a vertical. So look at number 6. I'm going to look at the degree. I have a 3x squared over an x squared. This behaves that the degree of both n and m are equal. So I'm going to look at the coefficients only. So the coefficients is going to be 3 over 1. So then y equal 3 is my horizontal asymptote. So at x equal 3, at y equal 3, I will have a horizontal asymptote. Last but not least, what happens if I have 3x and x squared? Well, m is 2 and n is 3. The degree of the numerator is higher, since x to the m over x to the n, m, and then n is greater than m. I do not know horizontal asymptotes. You don't have any. You don't have any horizontal asymptotes because it will fall under the first category, which is n greater than m, therefore no vertical asymptotes. Now, the graph of a rational function may not cross a vertical asymptote, but it may cross a horizontal. And that's exactly what we just said. So let's look at an example. Determine if the function crosses its horizontal asymptote. Well, the first thing is to determine, so step 1 is to determine the horizontal asymptote. Well, that means I'm going to look at the degree at both the numerator and denominator. So you have 2x squared over x squared. This will behave as a y equal 2 because I'm looking at the coefficients. So 2 would be the horizontal asymptote. Now, how would I determine if it crosses yes or no? Well, you're going to set f of x equal to 2 and solve for x. If to determine if there is an intersection. If it says if it's going to cross, that means is it going to intersect? That's what we're asking. So let's begin. So we have 2 is equal to 2x squared minus 4 over x squared minus 3x minus 4. Now what we have to do is to multiply top and bottom by the denominator so we can clear it out. 2 times x squared minus 3x minus 4 is equal to 2x squared minus 4. We clear it up, we clean it up, we get 2x squared minus 6x minus 8 is equal to 2x squared minus 4. You combine, so your x squared terms will cancel, one on the right, one on the left. You're left with negative 6x minus 8 is equal to negative 4. You bring the negative 4 to the other side. or let me see, you bring the negative 8 to the other side. So it's negative 6x is equal to positive 4. And then divide both sides by negative 6. You get x is equal to negative 2/3. So you're going to cross at negative 2/3 comma 2. So yes, it will cross the horizontal asymptote. So what we did was we set it equal to f of x and then determine if there was an x value that gives you that y value. So we talked about a vertical asymptote. We talked about a horizontal asymptote. Let's talk about slant. So all of these things happen when you have a rational function. How do we identify slant asymptotes? So a rational function will have a slant asymptote if the degree of the numerator is exactly 1 greater than. So what would be an example? If it's f of x is equal to x squared over x. This is only 1, x plus 1. See how the denominator is only 1 less, or the numerator is 1 more than the denominator? So what we want to do is we are going to create a quotient and find a slant asymptote will be an equation. So what does that mean? So notice here the degree of the numerator is 3. And then the degree of the denominator is 2. So that's exactly 1 greater than the degree of the denominator. So what I'm going to do is actually going to be polynomial long division to find the quotient or the equation of the slant asymptote. So let's do that together. So in section 2.4, we did polynomial long division. So we begin by having x squared minus 9 over 3x cubed. So how many times x squared goes into 3x cubed? It's 3x times. So 3x times x squared minus 9 is 3x cubed minus 27x. Then you have to put parentheses and a negative that you're going to distribute. So this is a negative and that becomes a plus. So this will cancel. You'll have a remainder of positive 27x. So how many times x squared goes into 27x? You don't. So this 27x becomes your remainder. But I don't care about the remainder. I only care about the quotient. What number did you get up top? That number was 3x. So this 3x is your slant asymptote, which is the equation. So you're going to have y equal 3x as a slant or oblique asymptote. That's another word for slant. So on the test or on your homework, you might see it as an oblique instead of a slant. So remember, we do not care about the remainder. We only care about the quotient. So it's y equal the quotient of that polynomial long division. Now the last part of the section is to be able to graph. Now we wish to graph a variety of rational functions. In order for us to be able to graph such rational functions, we need a few steps. So we need to do step 1 is going to be finding the x and y intercepts. Step 2, identify vertical asymptotes, horizontal, or even slant asymptotes. And then we want to see if the function crosses the horizontal or slant asymptote. If it does, yes or no. We want to check its symmetry, if it's symmetric towards the y or towards the origin. And the last step is step 4 is to plot points or test points. So This does take a long time to do because you're asked to do many things at once. And the last thing you want to do is actually check using your calculator. And you also want to use your calculator for these type of questions just to verify that you are on the right track. So let's start with question number 10. We wish to graph this rational function. So the first thing we want to do is find the x and y intercepts. So to find the x and y intercepts, I'll start with the x-intercepts. Let f of x is equal to 0. So that's 0 equal x squared minus x minus 5 over x squared minus 5x minus 6. When you're asked to find the x-intercepts, you only care about the numerator. So it's x squared minus x minus 5, set it equal to 0. Because this will cancel. You will cancel the denominators if you multiply it out. So then you're going to factor that numerator, and that's going to be x minus 3, x plus 2, set this equal to 0. I get x equal 3 and x equal negative 2. Those are my x-intercepts. So let's go ahead and plot these. Negative 2, 0, and 1, 2, 3. Okay, those are my x-intercepts. My y-intercept, you let x equal 0. So then f of 0 is going to be 0 squared minus 0 minus 5 over 0 squared minus 5 times 0 minus 6, or negative 5, 6, negative 5 and over a negative 6. Let me see here. 0, 0. And I think there's a typo on my notes. So this should be a 6. So let's fix that. So let me fix that. So let me fix the question. So let's fix the typo. So there's a typo on the notes. It should be x squared minus x minus 6 over x squared minus 5x minus 6. And that should be f of x. So again, my x-intercept, let the numerator equal to 0. So it's x squared minus x minus 6, set it equal to 0. Two numbers that multiply and give you negative 6, but add to negative 1. And we said that was negative 3 and 2. So it's x minus 3, x plus 2. Set it equal to 0 at x equal 3 and negative 2. That's where our x-intercepts are. So 3 comma 0, negative 2 comma 0. Now the y-intercept, you find f of 0 to be 0 squared minus 0 minus 6 over 0 squared minus 5 times 0 minus 6. That's going to be positive 1. So my y-intercept is a 0.01. Okay, that's what I have so far. We wish to find the vertical asymptotes. So these are the vertical asymptotes. That means set the denominator equal to 0. So you have x squared minus 5x minus 6, set that equal to 0. And then you're going to factor, of course, negative 6, negative 5. Two numbers that multiply and give you negative 6, but add to negative 5. That is negative 6 and 1. So you factor x minus 6, x plus 1. And that gives you a 0. I get x equals 6 and x equal negative 1 to be my vertical asymptotes. So if they're vertical asymptote at x equals 6, I'm going to go into, so this is going to be 2, 4, 6, 8, 10, 12, 14, and 16. So let me fix this. So we said 3 and negative 2. So negative 2 is right here, and 3 is about right here. Remember, they're by twos. And then we said 1. So 2, 4, 6, 8, 10. So 1 should be in the middle right here. And then the vertical asymptotes are going to be at negative 1 and 6. So at 6, at x equals 6, I'm going to have a vertical asymptote right here at x equals 6, and then another one at x equal negative 1. So that means right here, right in the middle between 0 and 2, that's my vertical asymptote at x equal negative 1. Now, if I have a horizontal asymptote, is if I have a degree, well, what's my degree? I have x squared minus x minus 6 over x squared minus 5x minus 6. The degrees are the same. So then if they are equal, then it's going to be the coefficients. So y equal 1 is my horizontal asymptote. So I'm going to go into 1 right here, which is my my y-intercept right here. So that's my horizontal asymptote. And then I'm going to say, okay, well, is it going to cross yes or no? And we're going to check. Let's check for symmetry. Because notice that it does intersect here at 0, 1. So it will cross the horizontal asymptote at y equal 1, right? We just saw it in our y-intercept. And now the next part is to check symmetry. So it's f of negative x should be equal to negative f of x. This is symmetric towards the origin. Let's see. So if we check, if we plug in a negative, I'll have f to the negative x is going to be equal to negative x squared minus negative x minus 6 is equal to negative x squared minus 5 times negative x minus 6. Then this becomes a positive x squared, a plus x minus 6, which is equal to positive x squared plus 5x minus 6. So it's not equal, and it's not the negative of the previous one. It's not the negative of the previous one, because if it's a negative of the previous one, if you factor out a negative from the top, it should be negative x squared plus x plus 6. And you don't have that. And on the bottom stayed the same as x squared minus 5x minus 6. So these two are not equal. So that means you do not have symmetry. You do not have symmetry across the origin or the y-axis because they're not equal either. So then what you'll have to left over is actually do some checkpoints and see, okay, what happens? So this is right here, a negative 1. So what happens before negative 1? So let's do some testing points. Let's check what happens when x is negative 3. What happens when x is past 4? We're at 4. What happens at 4? And then what happens after 6? So let's try 8 to determine the behavior of my function. So if I substitute f of negative 3, and let's substitute f of -3. This is scratch work. So on the test, you'll have plenty of room where you're going to be able to do your scratch work. F of -3 is going to be -3 squared minus a -3 minus 6 over a -3 squared minus 5 times -3 minus 6. So if I work it out, I get 9 plus 3 minus 6 over 9 plus 15 minus 6. So I get 6 over, I have a 9 plus 15. I have, let's see, if I open it up, so then I have 24 minus 6, which is 18. So it's 6 over 18, or 1/3. So 1/3 is in the positive direction. So at x equal -3, I'm going to be above. So I'm going to be right up top. So it's looking like tending to, oops. So if it's coming from negative infinity, it's going to pass -1, and then it's going to reach your horizontal asymptote right there. Now, what happens when I'm 4? So here I got positive 1/3, that's my y value. What happens at f equal 4? At f equal 4, if I plug it in, again, I'm doing scratch work. So f of 4 is going to be equal to 4 squared minus 4. There's my function right there. Minus 6 over 4 squared minus 5 times 4 minus 6. So then here I get 16 minus 4, which is 12. Minus 6 is 6 over 16 minus 20, it's a -4. -4 minus 6 is a -10, which is negative 0.60. So here it's negative 0.60. So at 4, I'm going to be down here. So then this, we have this shape. It's like a cubic right there. And then what happens at 8? Well, at f of 8, f of 8, at f of 8, it's going to be 8 squared minus 8 minus 6 over 8 squared minus 5 times 8 minus 6. So that's going to be 64 minus 8 minus 6. So if I have 64 minus 8 minus 6, that's going to be 50. So it's going to be 50 over 64 minus 40. 64 minus 40 minus 6. It's 18. So that's going to give you something positive. So 50 over 18 is going to be 2.77. So that means it's going to be above the x-axis. So the last part is to actually graph this on your calculator. So then we are going to check using our graphing calculator. So let's do that together. So I'm going to open up Calculate 84. So once you've done all of the values, then you are able to use your calculator on the test and check and verify. So right now we're going to be looking at the function of parentheses. Always make sure you have parentheses, x squared minus x minus 6, close parentheses, divided by x squared minus 5x minus 6, and close it. And then you're going to select graph. And then you're going to zoom in a little bit. And then that's exactly what we have on our lecture notes. Okay. But it's going to take us all those times to do. So we're going to do another example. So going back to the notes, we already learned how to start working with rationals. If we wish to graph, let me go to my notes and let me project them. Let me see here. So if we wish to graph the function f of x is equal to 2x over x squared minus 4. Step 1, find the x and y intercepts. Find the intercepts. So that's nice because the x-intercepts, you let f of x equal 0 for the numerator. So 0 is equal to 2x squared. That means that your x-intercept is at the point 0, 0. So let's go ahead and include it. Now the y-intercept is f of 0 is going to be 0 squared over 0 minus 4. This is going to be 0. So the y-intercept is also 0, 0. Now, step 2 is the vertical asymptotes. So the vertical asymptote is you look at the denominator, x squared minus 4, and set this equal to 0 and factor. This is a difference of squares. So my asymptotes will be at x equal 2 and x equal negative 2. So I'm going to do 1, 2, 3, 4, 5, negative 2. There's going to be an a vertical asymptote at x equal negative 2. And at x equal 2, you will have another asymptote, a vertical asymptote. Now, a horizontal asymptote is, notice that they have the same degree, so 2x squared over x squared. So you look at the coefficient. So the coefficient here is y equal to, so at y equal to 1, 2. So I'm going to do this color, pink, for my horizontal asymptote, and I want to see if it will cross, yes or no. So to determine if it crosses or not crosses, we can substitute the value 2 in there. So we can say, okay, well, so check if 2, if the graph will cross the horizontal asymptote. So to check, we have to set f of x equal to 2 and try to solve. So it's going to be 2 is equal to 2x squared over x squared minus 4. Now we would have to bring the 2 over and say, okay, well, that's 0 equals 2x squared over x squared minus 4 minus 2 over 1. And then see if we have an intersection. And if we combine like terms, I have to common denominators of x squared minus 4. Then you would notice that, let me go back. If I would want to solve here, cross the horizontal asymptote, we multiply both sides by x squared minus 4. So it's 2 times x squared minus 4 is equal to 2x squared. We'll have 2x squared minus 8 is equal to 2x squared. Your 2x squareds will cancel. Negative 8 does not equal 0. So then it will not cross the horizontal asymptotes. The next part we want to check is symmetry. So symmetry is find f of negative x if it also equals f of x. Well, let's see. If f is negative, you'll get f of negative x to be equal to 2 times negative x squared over negative x squared minus 4. And then what do you notice? Oh, it is equal. So then this is going to be symmetric to the y-axis, towards the y-axis. So then you're going to be testing points. You're going to test what happens at, so then you're going to do test points. So what happens before x equal negative 2, so negative 3. What happens between negative 2 and 0, so negative 1. What happens at 1 and what happens at 3. So you're split into different intervals. So you're going to find f of negative 1, f of negative 3, f of 1, and f of 3. So take a few moments and find f of negative 3, f of negative 1, f of 1, and f of 3. I'll give you guys a few seconds. So once you've plugged in your solutions, you should have gotten negative. When you plugged in a negative 3, you should have gotten a 3.6. When you plugged in a negative 1, you should have gotten negative 2/3. When you plugged in a 1, you should have gotten a negative 1/3. A negative 2/3. And when you got a 3, a 3.6. And this makes sense because we have symmetry. If we graph our function as it's approaching, x is going to our x equal negative 2 from the left side. This is going to go to positive infinity. Then we're going to have a parabola going down. And then we are going to have something that's, as x approaches positive infinity, it will reach your horizontal asymptote. And it has this behavior because we have symmetry. And then to check, you want to make sure that you look in your calculator. So we can go ahead and do that together. So there's calculate 84, and you're going to be placing y equal, you erase your first entry here. You're going to use parentheses, and you're going to place 2x squared here. Close parentheses divided by open parentheses, x squared minus 4. And then hit at graph. And then if you're going to zoom in a little bit, you'll notice it has that behavior. It's going to reach the horizontal asymptote, and then you'll have a parabolic going down way. Now this is a graph of question 11. Now the next thing we want to do is look at question 12. Question 12 is very similar. So we're going to do all of the steps. We're going to first find the intercepts. So f of 0 is going to be 0 squared. It's going to be 2 times 0 squared minus 8 times 0 plus 8 over 0 minus 3. You'll get 8 over negative 3. So my x-intercept is going to be the point negative 8 over 3 comma 0. Or if you want to round and use decimals, you may also do that. So 0 comma, that's my y-intercept, 0 comma negative 8/3. That's the y-intercept. The x-intercept, you're going to let 0 equal 2x squared minus 8x plus 8. So it's only the numerator. You're going to factor out a 2 or divide everything by 2. You get x squared minus 4x plus 4. Set this equal to 0 and factor. Two numbers that multiply and give you 4 but add to negative 4. That's negative 2 and negative 2. So you have x minus 2 squared is equal to 0. So my x-intercept is at 2 comma 0. So let's graph that. So 2 comma 0, be careful because when it's 2 comma 0, so this is 3, 6, 9, 12, and 15. So this is your x-intercept, and your y-intercept is negative down here. So negative 8 over 3 is a little bit more than 3. So then we have something right here. That's a negative 8/3 on the y value. Now we will say, okay, well, what are the vertical asymptotes? So at x minus 3, set this equal to 0. I get x equal 3. That's my vertical asymptote at x equal 3. So at x equal 3, I will have my first vertical asymptote. And then my horizontal asymptote is, well, I have a 2x squared over x minus 3. So I'm going to look at the degree. Because n is greater than m, no, I will not have horizontal asymptotes. But the degree of the numerator is 1 more, so it's going to be a slant asymptote or an oblique. So how do we know that? Because it's 1 degree more than on the numerator. So then we're going to have to do polynomial line division, where it's going to look like x minus 3 over 2x squared minus 8x plus 8. So how many times x goes into 2x squared? That's 2x times. So you'll get 2x squared minus 6x. Carry out the minus. This becomes a plus. This is a negative. They'll cancel. You'll have negative 2x plus 8. Now you're not done because how many times x goes into 2x? That's minus 2 times. And that's going to be negative 2x plus 6. And then you'll have a minus, and then you'll get a remainder of 2. But we don't care about the remainder. We only care about the quotient. So my asymptote, it's 2x minus 2. So my y equal 2x minus 2, that equation, it looks like this. You start at a y-intercept of negative 2, and then you're going to go up 2 over 1, up 2 over 1. So you'll have a slant asymptote. You'll have a slant asymptote at the equation y equal 2x minus 2. And then, well, you want to identify the symmetry. So how do we test it? F of negative x, is it equal to the same thing, or f of negative x is equal to negative the value? Well, what do we notice if we plugged in a negative? F of negative x is equal to 2 times negative x squared minus 8 times negative x plus 8 over negative x minus 3. That's 2x squared plus 8x plus 8 over negative x minus 3, which is not the same as if I factor. So this is not symmetric. So it's not symmetric to neither. Now to check is we want to be able to test points. And the way to test point is we want to know what happens at different locations. What happens X and Y, what happens before -8/3. So -3 at -1 at 4 and at 5. And you'll have different values where you can place them. Again, you don't have to have the same numbers as I do, but you want to be able to test points and check. So I'll give you a few moments and say, okay, what happens at f of -3, f of -1, f of 1, f of 4, and f of 5. So take a moment and I'll give you a few seconds to go ahead and punch this on your calculator. And you're more than welcome to check using your calculator during the test. So then I'm able to identify some of the values. Oh, when I'm 4, there's a typo. When I'm -3, it should be a -8.3. At -1, it's -4.5. At 1, I'm missing a value. What happens at 1? At 1, you get -1, and then at 4, I get +8, and at 5, I get 9. So the graph will look something like this. And then the way to check is using your calculator. So you want to be able to go back to your graphing calculator and check the graph. So that makes sure that you did the whole thing correct in the final answer. Now, the next thing is to use transformations to graph the function 1 over x minus 3 minus 1. So the first thing that you want to look at is you start with the original function. So the original function is 1 over x. We know that 1 over x, it has this behavior. As x approaches 0, you'll have an asymptote here. So this is the graph of 1 over x. So you begin with the graph of 1 over x. So if I graph 1 over x, it's going to have, oh, let me fix that. So 1 over x looks like this. Now we have different asymptotes. And notice that you will have a new vertical asymptote at x equal +3. So what you do is you're going to now put a vertical asymptote at x equal +3. And so at x equal 3, and a horizontal asymptote at what happens when I have, if I rewrite this as 1 over x minus 3 minus x minus 3 over x minus 3, because this is technically 1. And then if I combine like terms, I get x minus 3 over x minus 3 squared. Or excuse me, you'll have it at, this would be a minus, and this would be a plus, because this is negative on the outside. You distribute the negative x plus 3 over x minus 3. It's when you subtract the fractions like this. This is a minus c over b with the common denominator. So then this becomes negative x plus 3 over x minus 3. And you have a horizontal asymptote. You look at the degree, you have a negative x over an x. This is a -1. So now I will have a horizontal asymptote at -1, and the graph doesn't do anything else but it reaches its asymptote. So then all you have to do is place the vertical asymptotes and the horizontal. So that means you shift to the right 3 units. So there's your shift to the right, the -3, and then down 1 because of the vertical, the -1, minus k. So then what you have to do is there's your horizontal asymptote at -1, and then x equal 3. And then your graph still looks the same. So it's reaching those asymptotes. And there is your graph right there. Now, the last part of this section is to use rational functions for applications. So Young's rule uses a formula for calculating the approximate dosage for a child given an adult dosage. For an adult dosage of D, the child dosage is Cx. So this is the formula that is calculated to approximate the child dosage versus the adult. X is the child's age that ranges between 2 and 13. We want to determine the horizontal asymptote of the function. So just the way as is, if we look at dx over x plus 12, we would say, okay, we would have to look at the degree. So the degree are both the same. So then we look at the coefficients, which is d over 1. And what does that mean? At y is equal to d, that means that the child dosage or dose will approach the adult, but never equal, but never exactly the same. Okay. What is the vertical asymptote of the function? Well, on the denominator, x plus 12, set it equal to 0. X equals to -12. That would be the vertical asymptote. And then part C, it's saying for an adult dosage of 50 milligrams, so they're already telling you what D is. D is going to be 50. What is the approximation dosage for a 9-year-old? So there's X. X is 9. So you're looking for C of 9. So C of 9 is going to be 50 times 9 over 9 plus 12. So that's going to be 450 divided by 21, which is going to be approximately 21.4 milligrams. Now, if we wish to graph the function 50x over x plus 12, we would notice that we have a horizontal asymptote at d equal 50, because that's the dosage given, 50. And it will have a vertical asymptote at x equal -12. Okay. And that's the graph of 50x over x plus 12 if we were to graph this on our graphing calculator. And with that, we finish section 2.5. Thank you so much, and I'll see you guys next time. Bye-bye.